Hello everyone and welcome back. So we got one more problem to do. And this one we have, once again, a rectangular bar. Like, when are they going to give us a triangular bar? And the answer is never. Not right now, at least. Goodness, triangle, that'd be a nightmare. I don't want to think about that, so I'm not going to think about it. So, this rectangular bar has a width of 3 inches and a thickness of 2 inches. Haha, area. The normal stress on the plane AB of the rectangular block shown is 6 KSI when that load P is applied. Okay, so what we want to find is, first off, what is the magnitude of load P? Then, what is the shear stress on plane AB? And finally, the maximum normal and shear stresses in the block at any possible orientation. Okay, earlier on we had that sigma max and tau max equation. Those are going to be helpful. So with that in mind, these steps kind of lead you through the problem. I want you to go grab a buddy, grab a stuffed animal, grab a duck, and try to do this problem. If you get stuck, you come back and you can follow through the rest of it with me. So 3, 2, 1. Through the power of movie magic, you have now paused and tried the problem, and now you're back. Or you didn't pause and you're just like, I'm just going to watch it straight through. Shame on you. Can't believe you. Oh, well, you can do what you want. It's a video. So the general equation for normal stress is this. But, we're not even angled to begin with. We just need to find that load P is. But we'll go ahead and calculate theta. So we need to know what theta is. We have theta for that plane. We're going to calculate the shear stress. Okay. Now we can get the cross-sectional area fairly simply. It's simply 3 inches times 2 inches, length times height, width times thickness. And we know what the normal stress on plane AB is, and it's given as 6 KSI. So using our earlier equation, we solve for the load. Let me just jump back a little bit. We're using this equation right here. We get the angle, and then once we have the angle, we can solve for P, which isn't too terribly bad. We can just multiply both sides by this, so we get sigma times 2a, and then divide by 1 plus cosine 2 theta. And we should have P by itself. Okay, bringing it back. So here it is. If you're wondering why we have an equal sign and not like a less than equals to sign, because it told us that it's exactly 6 KSI on this plane. We're not trying to solve for some sort of condition. And if we're careful, what we get is 56.25 kips, which is 56,250 kilopounds per square inch. Okay, kilopounds per square inch. If you multiply KSI, this is kilopounds. KSI is kilopounds per square inch. Sorry. If you multiply inches by KSI, you're going to pop out with kips. The K right there just stands for 1,000. And we're going to round that to 56.3 because we only need 3 sig figs. Okay, now we've got to find the shear stress on that plane. So we have our shear stress in terms of our general angle, theta. And if we then plug in everything we know the angle, we know what the area is, we know what this load is, we can easily get what our shear stress on that plane is, which is going to be 4.5 KSI. This is the angle we got from using our slope triangle. This is the load we got because we knew what the normal stress was. And here is our area from the thickness and the width that was given to us. Now it says, okay, what is the max normal stress and shear stress for any given configuration? And we have a nice equation for that. First off, sigma max is always just our regular normal stress equation. We plug in the 56.25 kilopounds, 6 inches, and we get that it would be 9.38 kilopounds per square inch. And then we also know that tau max is just going to be simply half of that. So we divide this by 2 and we get the same. We get 4.69 kilopounds per square inch. And that's it. This one right here, it's a lifesaver equation, especially if you connect it to this and realize that it's just half of sigma max. That will save you a little bit of time, and it's a good rule of thumb to check. So I hope this helps you. We have done quite a few problems in these inclined planes. Hopefully you're feeling more like you've mastered this material, and we will continue to go from there. So have a wonderful day. Bye-bye.